Alright, for part 2 for the OLED display, instead of printing out a font, I decided to I'm going to print out a string. It's the same difference. And you can see here to the right, all I did was take this command, SSD1306 write text command, and also I created a pointer to the string on board, and then just use it as a parameter in this write text command. And this command will go down explore. And this is just the video showing that was when I flashed it to the board. So digging down into this write text command, right click. You can see here that it has one parameter of the string, and it creates a character pointer and an unsigned int for the loop. And the first line here is checking for the null character, so it's just making sure that you have characters in your string, you have a string there for it to read. And then this line here, as long as the string is less than hex 7f. So this is make sure this is a valid ASCII character. If you go to the any ASCII table, just Google it, and you look up the table, you'll see that the last ASCII character is 7f. So basically that line is just making sure that any of the characters that are in your string are valid ASCII characters, and as long as they're less than 7f, they're going to be valid characters, ASCII type characters. And then the next line sets the character pointer equal to the font table. So this line points the character pointer at the font table found in the font C file. And so I'll go to that table here. And you see here we have an array, and it's an array of pointers, and then right click on one of these pointers here, see what it's pointing to. You see that it's pointing to another array, the value of hex 20. So if you go to your ASCII table, look up hex 20, you see that it's a space, and you can see here that it's the space. So it's basically printing out each one of the bits to create a space, and obviously these are all zeros. So going back to the write text command, we're at this line here with the character pointer pointing towards the font table, which is a list of pointers which themselves point to character arrays that actually print out each character. And the parameter here is a string minus 32. So I was always wondering what's with 32, why is it subtracting 32? And then once again you look to your ASCII table and you see here we're 32. If you look at the values here ahead of 32, like 0 through 31, have all these types of commands and stuff that we don't need for the display. We're not printing any of this stuff out. This hasn't anything to do with fonts. So that's why they're subtracting all this and starting at 32 here, where you can see we have all the characters that we're going to use in the display, including our letters and numbers, upper and lower case, and special characters that we're going to need in the display. Hence the minus 32 here. So the next line down here is a for loop, and it's going to start incrementing the pointer through the each letter in our string. And it's basically checking for a null. If there's no null, then it'll continue writing the data, each letter in the string. Because I is set to 1, and as long as I is less than or equal to the character pointer, whatever it's pointing to. In this case, it's going to be, you know, one of the ASCII letters or values, and those are going to be greater than 1. So this will continue through the loop until it hits a null character, which is 0, and then this will no longer be a valid state. It won't be true anymore. I won't be less than or equal to 0, and it'll stop because it know it's gotten to the end of the string. And so as it goes through the array, it prints each character using the write data function here. So if we go down to it, you can see here the write data function has the actual, you know, data of the font that we're trying to print to the screen as a parameter. And this is going to be the basically where we're going to actually transmit the byte over the USART interface to the 1306, you know, controller pin on the display. So this is basically the nitty-gritty of the USART, is what the write data function does, and using our chips or our command select pin here to, you know, tells whether it's the data, the byte that we're sending as a command, or if it's actual data, and then selecting the actual USART that we're using on the board. I think, remember, is USART D0 was the one that's hardwired on my demo board. So whatever USART is, you know, hardwired to your display controller, this is going to select it, and then send the transmit the actual byte over the USART to the display, the 1306 controller, display controller chip. And then, so it's after it's finished, it's run to the null character at the end of your string, then it jumps out of the for loop, and so this line here is if this value up here, if this was not true, if this is not a valid, the character is not a valid ASCII character, it'll skip this whole for loop and just write out a space, an empty space, a blank to the display, because it's not a valid, you know, ASCII character. And then obviously this is going to increment the string to the so I guess, and increment the string based on this statement. Remember, as long as there's no null character in the string, then it's going to keep going through here and writing each one of the letters out until this statement becomes becomes not true, or or when it hits a null character. That's it. It's done. Now this is going over this. I think I got it wrong. This is because this loop here is not checking for a null character, it's checking for a valid ASCII character. And if it doesn't get a valid ASCII character, then it just prints a blank. It's this statement up here that's checking for a null character. So I probably should put this as it's checking for an ASCII character, and then this other statement is checking for the null. Anyways, so back to the main. So that gives us a general idea of what's going on with the write text command at a basic level. Now to initiate, before it even gets to this point, you have to initiate your LED display, and that's done with this command. And once again, we got a define statement kind of to another function. And this one is kind of a function that's going to point to another even more base initialization function, which is this down here, this SSD 1306 initialization function. And basically it'll start with the first thing it does is it does a hard reset on the 1306 chip. And when it does a hard reset, brings the reset pin low. The reset pin is connected, whatever is connected to whatever pin is on the microcontroller, and it brings it low. And as long as it has to do it at least for a minimum of 3 microseconds, and then it'll bring it back high, and that starts the reset. So when the chip, the S1306, does reset, it'll leave it in this default mode where the display is off, 120 by 64 display mode, normal segment and display data column address and row address mapping, segment 0 map to address 00H, and COM0 map to address 00H. So I'll go over that in a second, but basically sets everything, I think, to page 0 and the far left corner. Now this can all be manipulated depending on how you initialize the display. You can start it at the bottom and have it go up to the top. You start from the right, go to left, left to right. You can do all kinds of crazy manipulations with it, but I always stick with the reset values as much as possible to try and understand what the heck's going on. And so this is what you're left with after the reset. Shift register data clear in the serial interface. I guess it clears the buffer out. Display start line is set at display RAM address 0. Like I said, up in the top left corner, I believe. Column address counter is set to 0, to the far left. Normal scan direction of outputs from left to right. And it sets the control contrast control register to 7FH. Always make sure, sometimes if you have this set wrong, your display might actually be working and it looks like it's not because it's blank, because your contrast isn't set properly. And then it sets it in normal display mode, which is A4H command. And then basically you can set the display mode so that every pixel is lit up, or for the normal mode A4H, the pixels will not be lit up, but it's in normal mode, ready to go. And then the interface initialization for your USART. We'll get into that probably in another video. Where you set everything, or when USART gets initialized, everything gets set up so that it's functioning properly. And then you get into a whole list of commands here, initialization commands, like setting the multiplex ratio. Don't know what that is yet. The default is 63. Shift mapping RAM counter. This command can shift the display horizontally, so you can set the offset of the display where the actual I guess pointer starts displaying pixels. If you want to shift it to the right, you can set an offset in there. But we're not messing with any of this. We want everything displayed normally. We're just going to follow what they have set in this, these commands set in the initialization function. Set the RAM display start line. You have a range 0 to hex 3F, and that shifts the display to the right. The column address. The command set segment remap, column 127 segment 0. This command just sets the column 8 bits higher, or sets the starting and ending address in the RAM of the columns.